And so the idea of these possible orbits is that the center of this circular orbit, of these circular orbits, if you think of them like a disk, imagine that like a frisbee disc or a blade or something like that cutting right through the Earth. The center of that disk is somewhere around here, isn't it? Around in the center there. Same with this disk here, somewhere around that center. Well, exactly around that center. Okay, right at that point there. The center of these disks is about here. This disk, for this disk here, the center is there, and the center of this disk here is there, not the center of the Earth. The centers don't coincide with the center of the Earth, and there's a problem there, because where is the force, where is the acceleration towards when we're talking about this gravitation that provides the centripetal force that keeps this object in uniform circular motion? Where is it toward? It's toward the center of the Earth, isn't it? And very quickly, what's going to happen is this: as soon as you let go of this this satellite, it's going to move down and try and coincide with the center of the Earth, and very quickly crash or go out external to our orbit, and we don't want that to happen. We looked at a video about geostationary satellites, how they orbit above the same point on the Earth, and that they have a period of 24 hours. If you can imagine this situation, though, oh, actually, I better draw this. Where, what's the condition of a geostationary satellite? Does anybody know straight away? Yeah, so the first one is that the orbital period needs to be the same as the time for one rotation of the Earth. And there's another one. Geostationary means what? Break the word up. Yeah, stationary. Not dynamic, doesn't move, and geo meaning Earth, of Earth. Okay, so now it wants to stay above the same spot on the Earth. So imagine as if it's like it's tethered to some cable. There's our satellite there. Okay, I don't want to. I'll put it upside down. There's our satellite. It's tethered to some cable that's connected to the center of the Earth. In order for that to stay above the same point on the Earth, it must rotate with the equator or above the equator. Can everybody see why that is? It must rotate above the equator. Imagine then if I had a cable, a geostationary cable that we have to go from the center, but going from the center in this direction. What's going to change? What's going to happen here? Can you see that if it's rotating in a disk that kind of looks like over in this direction or something like that? I hope that's not too confusing. I'll delete it in a second. But what's going to happen is the Earth is going to revolve around underneath it due to the Earth's rotation. And so it's not geostationary because the Earth's moving underneath it. So geostationary satellites must orbit above the equator. We were going to do a calculation here. What is the radius? So the question is, we're going from this here. What is the radius of the So we're doing this calculation. Quiet, please. Those people that aren't taking notes, please take notes. Don't rely on these notes. They could fail. I could forget to press record at some point. Yes. What's the first thing that we have to know? Of course, we know the... Quiet, please, now. We know the mass of the Earth. That's fixed. 4 pi squared, we know. G, this is the gravitational constant. We need to know T. The period of motion is going to be 24 hours. Which is going to be equal to 24 by 60 seconds, isn't it? Which is equal to, we did this calculation in the last 86,400, thank you. Not 86 point, 86,400. 86,400 seconds in 24 hours in one day. It's not quite 24 hours, the period of rotation of the Earth, but it's very close to 23.5 something, I don't know. Yeah. Okay, so I'm going to leave r cubed as it is, so I don't have to write the cube root every time. 8.64, 10 to the 4. That's t squared times g minus 11, not plus 11, times the mass of the Earth. All over 4 times pi squared. And somebody did jump the gun, did the... yes, okay, yep, thank you. Is equal to... Thank you, somebody's calculated it for me very quick. 7.54 by 10 to the 22. 7.54. Does anybody concur? 10 to the 22. That's r cubed, of course. So r is going to equal to the cube root of that number. Thank you. This looks good. 4.2 by 10 to the 8. Ten to the 7. 4.2, what was it? Oh, they got 2.5. 10 to the 7 meters. Quite a large radius. What's wrong with this? That's not the altitude. Yes. Altitude. It's the distance from the center of the Earth, of course, and so we have to do another calculation. Altitude. Altitude, yes, equals r minus the radius of the Earth, r sub e, equals 4.225 by 10 to the 7 meters minus 6.37. Now they say 1 here, and there was dispute earlier, and we worked it out. 337. Oh no, sorry, beg your pardon. This was in a later question. This is 378. Beg your pardon. By 10 to the power of 6 meters. 35,872 kilometers. Quite high. Very high, in fact, considering aeroplanes fly at about 10 kilometres high. So that's the geostationary altitude. I'll just leave that there for a second for people to finish up. Now I've just done a calculation to show you the altitude of a geostationary orbit. What have I implied by saying that, doing that calculation? that there is only one possible orbit altitude for a geostationary satellite. Only one possible orbit for a geostationary satellite. Let's have a look at launching these things. And think about this situation where, and I'm going to choose North America, or this is something like that. That's Florida there. Looks something like that. They launch in this direction. Why? Abel. Shh. Fastest at the equator, yeah. So do you know how fast the Earth is spinning the equator? So if you're standing at that point there at Florida, and imagine, Florida is very close to the equator, it's quite tropical there. At the equator, the rotation of the Earth, anybody want to take a guess? The speed that we are doing now, approximately? 23.7 watts. Kilometers per second? That's a lot. Rotational speed of the Earth is approximately 500 meters per second at the equator. Approximately. That's a kilometer every second. It's quite fast. And we were talking in the last class about somebody said, okay, so what happens if the Earth all of a sudden stops rotating to us, like immediately just stops rotating? Oh, right, okay, so those are the consequences that happen later on. Yeah, the sun won't go down, obviously, so it just stay where it is now. Yes, that's later on, but you've got a bigger problem than that. Yeah, wouldn't you like crash into walls and stuff? Yes, absolutely. So the Earth. So what's happening? What are we doing with the Earth at the moment? We're moving at 500 meters a second as it turns, and we know that it rotates in a west to east direction, doesn't it? It rotates like that from the west to the east. So which way is east? It's behind us, isn't it? About that direction. So we're rotating in that direction at about 500 meters per second relative to outer space. And the Earth underneath us stops. What do? We keep going at the same speed, don't we? Keep going at the same speed. So the Earth stops, we keep going at the same speed. What does the wall behind us appear to do? And you wouldn't have time to think about it. Okay? Because all of a sudden the wall would come up and hit us in the back of the head. In fact, we'd probably all go through the wall. And yeah, it'd be a big mess. A big mess. And terrible, absolutely terrible. We'd appear to travel towards that wall at 500 meters a second, traveling at a kilometer in 2 seconds. That's faster than you guys have ever traveled before at that wall. Splat. Probably go through the wall. I don't know. With all of our mass hitting that wall all at once. Yeah. It's about the radius, 6378 kilometres. Kilometres per hour, 1800 kilometres per hour. Yeah. That's at the equator. Oh, you've done a calculation, got it just about right, yeah. That's at the equator. Yeah. I like to round it up. 434 metres per second is right. And I round it up because I remember that number. I say it's about 500 metres per second. So, yeah. So, we need to know, so what am I getting to here? The rotation of the Earth provides some of the initial velocity relative to space, remember. If we launch from west to east, and so less fuel is required. It takes more fuel to get up to 1800. Somebody's calculated about 1800 kilometres an hour in 500 metres per second, and so it takes some fuel to get to that speed, of course, to propel something that massive to that speed. So they want to save that fuel. Low altitude polar orbits. What do you think that means? I'd say no idea because it's Friday. Have a go at it. Yeah, yeah, kind of goes around the poles if the Earth's tilted. Yeah, in a north to south direction. This kind of orbit here, very low altitude compared to geostationary satellites. What's the benefits here? Or what are the benefits here? You can see the poles, yes. Geostationary satellites can't even look at the poles. If the satellite is actually designed to take photographs, and there are satellites up there that are designed just to scan areas for visual images. Their altitude have another look at that. What sort of motion's going on there? So the satellite's moving around the Earth. What's the Earth doing underneath it? It's rotating as well, isn't it? How is that going to help us? And think about the period of the rotation. This, I'll just tell you now that these do one of these laps in about an hour and a half, just a little bit less than, or just a bit over an hour and a half. How far is the Earth going to have travelled in that time? Not far. It does a full rotation in 24 hours, doesn't it? So, wait, one of 24? Yeah. So imagine the Earth's the satellite scans across this sort of area here, on that orbit. In the next orbit, it can scan right next to it, and the next orbit it can scan, and so on and so forth, okay? And as the Earth rotates underneath this satellite, it can scan all of the Earth in fine detail. Yes. At what altitude? Between 400 and 600 kilometres altitude for the International Space Station. So they're not very high, relatively. When we're talking about these satellites and where the space shuttle orbits anywhere between maybe 350 and 600 kilometres. These guys here are about 850 kilometres. They're a little bit higher, okay? And remember, we're talking geostationary. They're way out, 35,000 kilometres. So much, much bigger, okay? These satellites, uh, 14.2 times a day. Got a question for you. Period of this low orbit satellite, 24 times 60 gives us seconds in a day. 14.2 out of that. 14.2. Oh, 1.69 hours. Six 6,000 seconds. Which formula are we going to use? Where does it come from? R cubed equals the period squared times big G, gravitational constant, over 4 pi squared, 4 times pi squared. I'll just go straight to the R this time. R equals 7.2 by 10 to the 6 meters. This is the orbital radius again. Orbital radius of the satellite. Radius, remember, altitude. Question? Right, okay, sorry. Radius 7.2 by 10 to the 6. And this is the discrepancy we were wondering about before. I think it comes out in the book, it says 6.371 by 10 to the 6. Can somebody explain how we had a radius of the Earth earlier? It was 6.378 by 10 to the 6. What's going on there? No, it's not a perfect sphere. Why is that? How do we know that? Yeah, that's right. The Earth kind of bulges, doesn't it, at the center, at the equator. And because of its spin, because of this massive spin, it bulges at the equator, tends to bulge at the equator. And so this is the polar measurement, and 6378 is the equatorial measurement. Altitude is about 829 kilometers. It's not that high. Higher than the Space Shuttle and the International Space Station orbit, but not that high. I want to know the velocity at this height. Remember, the velocity and the radius are dependent on each other. Two pi radius is, remember, that's the orbital radius to the center of the Earth we've got to use. 10 to the 6. I better put a times in there to be complete. All over the period of the satellite, which was our time in seconds, 6.0845 by 10 to the 3 seconds. That's our speed in meters per second. Times by 3.6 will give us kilometers per hour. 26,000 kilometers per hour. That's not far off of 8 kilometers a second.